There is a fish moving through water right now that has never seen sunlight, has never felt warmth from above, and has never once in its life swum near the surface where the sky begins. It lives in a world that begins where light ends, in water so cold and so compressed that no surface creature could survive more than seconds in it, in a darkness so total and so permanent that the concept of day and night simply does not exist. And yet the deep sea is not empty. It is one of the most biologically diverse environments on Earth, filled with creatures that have solved the problem of living without the sun in ways so strange and so varied that even after a century of deep ocean exploration, researchers continue to pull up animals that challenge everything we think we understand about what life requires. Tonight, we will descend gently through all of it, through the layers of fading light, through the bodies that make their own illumination in the dark, through the strange economies of a world that runs on food falling from above, and into the quieter questions about minds and lives conducted entirely beyond the reach of the star that powers almost everything else alive. So let the room grow still and deep around you. Let the warmth above the covers feel like the sunlit surface receding slowly as you drift downward into the dark, and follow the light down past the point where it disappears, into the world that learned to live without it. The ocean does not go dark all at once. It fades in stages, each stage taking something away from the organisms that have learned to use what remains, until the final light is gone entirely and the deep begins in earnest. Understanding how deep-sea fish survive without sunlight requires beginning at the surface, where sunlight is most abundant, and following the light downward through its progressive disappearance, because the biology of the fish in each layer has been shaped by exactly how much light that layer receives and what can be done with it. The sunlit zone, the epipelagic, extends from the surface down to approximately 200 meters, the depth at which photosynthesis becomes energetically impossible because the light is too dim to drive it. This zone contains the ocean's primary productivity, the phytoplankton and zooplankton communities whose photosynthesis and grazing form the base of the marine food web. And the fish that live here are the familiar ones: tuna, mackerel, herring, the species whose bodies are tuned for life in a world of abundant light, visual predation, and the chase of prey in 3 dimensions through clear lit water. The fish of the sunlit zone are not our concern tonight. They are the world above the one we are descending into. Below 200 meters lies the twilight zone, the mesopelagic, extending to approximately 1,000 meters. In this layer, sunlight still penetrates, but in quantities too small for photosynthesis, fading from the deep blue of the lower epipelagic to a dim, barely perceptible blue-green glow that provides no warmth and almost no illumination by surface standards, but is not yet zero. A mesopelagic is the most biologically productive deep-sea layer in terms of fish biomass, containing the lanternfishes, hatchetfishes, bristlemouths, and dozens of other families that have evolved specifically to exploit this in-between world of near darkness. Many mesopelagic fish perform the largest daily migration on Earth, ascending toward the surface at night to feed in the productive surface waters, and descending again before dawn to shelter in the dimmer water below. A vertical migration driven by the trade-off between the food available near the surface and the visual predation risk that daylight brings. At their deepest daytime depths, these fish experience light levels measured in nanowatts per square centimeter, a quantity of light so small it strains the concept of illumination. Below 1,000 meters, in the bathypelagic zone, even this residual twilight is gone. The water here is in permanent, absolute darkness that no sunlight has ever reached, and no sunlight will ever reach, regardless of season, latitude, or time of day. The temperature is a nearly constant 2 to 4 degrees Celsius. The pressure at 1,000 meters is 100 atmospheres, enough to crush a sealed metal container. At 2,000 meters, it is 200 atmospheres. At the deepest ocean trenches, exceeding 10,000 meters, the pressure reaches more than 1,000 atmospheres. The fish that live here have dispensed with almost every adaptation developed by their surface relatives for a world of light, warmth, and buoyancy, and replaced them with a completely different set of solutions for a world defined by darkness, cold, pressure, and scarcity. They are, in the most literal sense, a different way of being a fish. The bodies of deep-sea fish are shaped by the same physical laws as surface fish, but the specific pressures of the deep ocean environment have pushed evolution towards solutions that look at first encounter almost like the work of a different designer altogether. The most immediately striking feature of many deep-sea fish is their size relative to their body structure. Reduced musculature, gelatinous tissue, minimal bone, and in some species a body that is largely water, held together by a thin skin with barely any structural skeleton beneath it. These features are not deficiencies, but adaptations, each one a response to the specific constraints of deep ocean life, in ways that become clear when the full picture of that environment is considered. The reduction of skeletal mineralization in many deep-sea fish reflects both the energetic cost of building and maintaining bone and the pressure physics of the deep ocean. At great depths, maintaining a rigid, air-filled swim bladder of the kind that shallow-water fish use for buoyancy control becomes extremely energetically expensive or physically impossible, because the gas inside must be maintained at pressures that require specialized secretory organs working continuously against the enormous pressure differential. Many deep-sea fish have either eliminated the swim bladder entirely or replaced the gas within it with oil or wax esters, which are incompressible and do not require energy to maintain against pressure. Without the need for a rigid gas-filled cavity, the constraint on overall body rigidity is relaxed, and many deep-sea fish have evolved body plans of near-neutral buoyancy, achieved through the accumulation of low-density gelatinous tissue and the reduction of dense bone and muscle, producing bodies that float passively at depth without any active buoyancy work. The eyes of deep-sea fish show some of the most dramatic evolutionary specializations found anywhere in vertebrate biology, and the variety of solutions across different species reflects the different amounts and qualities of light available at different depths. In the twilight zone, where dim downwelling light still filters through from above, many species have evolved enormous upward-facing eyes with very large pupils and retinas dominated by rod photoreceptors, tuned to detect the faint silhouettes of prey against the slightly lighter water above. The tubular eyes of the barrel-eye fish, Macropinna microstoma, are among the most extreme examples, pointing straight upward through a transparent dome of fluid that serves as the head, collecting maximum light from above while the fish hangs motionless in the water column below. These eyes were for a long time assumed to be fixed upward-pointing structures until researchers using remotely operated vehicle cameras observed that the eyeballs can in fact rotate within the transparent dome, allowing the fish to look forward as well as upward, a discovery that resolved decades of confusion about how the fish could see anything it was about to eat. In the completely dark bathypelagic zone, where there is no downwelling light at all, the visual challenge changes from detecting faint light to detecting the bioluminescence produced by other organisms. The eyes of many bathypelagic fish are accordingly tuned for sensitivity to the specific blue-green wavelengths that bioluminescence most commonly produces, with visual pigments whose peak absorption matches the wavelength of light most abundant in the deep ocean environment. Some species have evolved a different solution entirely, reducing the eyes to vestigial structures and relying on mechanosensory systems to detect prey. The lateral line system, which detects water movement and pressure waves and is present in all fish, becomes particularly important in the lightless deep ocean, where the approach of a large body or the movement of prey through the water column produces pressure waves that can be detected at distances of meters, even in complete darkness. The deep ocean is acoustically and mechanosensory rich, even when it is optically empty, and the fish that live there have evolved senses that exploit this richness. In the permanent darkness of the deep ocean, light exists. Not sunlight, not reflected light from any external source, but light generated by the organisms themselves through bioluminescence, the biochemical production of photons by living tissue. Bioluminescence is not unusual in the deep ocean. It is the norm. Estimates based on deep-sea surveys suggest that more than 75% of all deep-sea organisms are capable of producing their own light in some form, making the dark ocean not a lightless void, but a sparsely spangled, constantly flickering, biologically generated light show of extraordinary diversity and biological sophistication. Understanding deep-sea fish life requires understanding bioluminescence, because light production is central to how these animals hunt, communicate, avoid predators, and find mates in an environment where no other light source exists. The chemistry of bioluminescence is based on the reaction between a light-emitting molecule called luciferin and an enzyme called luciferase, which catalyzes the oxidation of luciferin to produce an electronically excited intermediate that releases energy as a photon of light as it returns to its ground state. The specific luciferin and luciferase molecules vary between different taxonomic groups, and the independent evolution of bioluminescence has occurred at least 40 to 50 times across the tree of life, reflecting how useful the ability to produce light is in the dark ocean environment. In fish specifically, bioluminescence has evolved independently at least 27 times in different lineages, producing an enormous variety of light-producing organs called photophores that differ in structure, control, and function between species. The convergence of so many independent evolutionary lineages on the same biochemical solution to the problem of living in the dark is one of the most striking examples of convergent evolution in biology. The uses of bioluminescence in deep-sea fish fall into three broad categories that often overlap in the same animal. Counterillumination is the use of light to cancel the fish's own silhouette against the dim, downwelling light from above, making the fish invisible to predators looking upward from below. Many mesopelagic fish, including the hatchetfishes and lanternfishes, carry rows of photophores along their belly surfaces that produce downward-directed light, calibrated to match the intensity and color of the ambient downwelling light at their current depth, effectively making them transparent to a predator's upward gaze. The precision of this counter-illumination system is remarkable. The fish can adjust the intensity of its ventral photophores in real time, as it moves through layers of different ambient brightness, matching the downwelling light continuously. Some species have even evolved photophores that can produce polarized light to match the polarization of the downwelling light, closing a potential detection channel that polarization-sensitive predators might otherwise exploit. Bioluminescence for predation takes a different form. The anglerfish, perhaps the most iconic deep-sea predator, carries a modified dorsal spine tipped with a luminescent lure called the esca, which dangles in front of the fish's enormous, tooth-studded mouth and produces a glow that attracts prey curious enough to investigate a light source in an otherwise dark environment. The light production in the anglerfish esca is not generated by the fish's own biochemistry, but by symbiotic bacteria housed in the lure tissue. Bacteria that produce light continuously as a byproduct of their metabolism, and that the fish maintains, presumably through the provisioning of nutrients, as a living light organ. The fish exercises control over the apparent intensity of the lure, not by controlling the bacteria's light output directly, but by controlling blood flow and shutter-like tissue surrounding the esca that can dim or expose the bacterial light as the hunting situation requires. The anglerfish is not producing light. It is farming light-producing bacteria and deploying them as a hunting tool. The deep-sea dragonfish, family Stomiidae, have evolved a solution to the predation problem that goes further than simple luminescent lures. Many species carry suborbital light organs beneath their eyes that produce red light rather than the blue-green light that most bioluminescent organisms produce. This is significant because the visual pigments of most deep-sea organisms are tuned to the blue-green wavelengths that both bioluminescence and residual downwelling light produce, and are essentially blind to red light. A dragonfish that illuminates the water ahead of it with red light is using a searchlight that it can see but that its prey cannot, hunting in a private visual spectrum that the deep ocean's other inhabitants have no ability to detect. The ability to see red light and to use it for hunting represents an evolutionary arms race breakout, a move to a new sensory channel not yet occupied by prey defenses. And the visual pigments of dragonfish that can see their own red illumination are different enough from those of other deep-sea fish to require explanation as a specific adaptation rather than a coincidental feature. The deep ocean has no photosynthesis. Without light to drive the conversion of carbon dioxide and water into sugars, the entire energy base of the deep ocean food web must come from somewhere else, and that somewhere else is the surface ocean above. The connection between the sunlit surface and the permanent dark of the deep is a continuous slow rain of organic material called marine snow, a term that captures both the appearance and the behavior of the fine particles of dead phytoplankton, zooplankton fecal pellets, shed mucus, and organic aggregates that form in the surface waters and sink slowly through the water column, carrying the chemical energy of surface photosynthesis downward toward the deep ocean floor. Marine snow is the primary food supply of the deep ocean ecosystem, and the biology of deep-sea fish is organized at every level around the challenge of extracting energy from this dilute, unpredictable, and often inadequate supply. The flux of marine snow decreases exponentially with depth as the particles are consumed, decomposed, and remineralized during their slow descent. By the time organic particles reach the deep bathypelagic zone, typically below 2,000 meters, they represent only a tiny fraction of the organic matter that left the surface, with most of the energy having been consumed by organisms in the mesopelagic zone during the particle's descent. This means that the deeper you go in the ocean, the less food is available per unit volume, and the biology of deep-sea fish reflects this energy gradient with striking clarity. The deepest fish are generally the most energy-conserved, the least active, and the most specialized for infrequent, opportunistic feeding. The metabolic rates of fish at 2 or 3 kilometers depth are among the lowest recorded for any vertebrate, reflecting a metabolic economy so tight that the fish can survive on food encounters that would represent starvation rations for any surface fish of comparable size. The mid-water fish of the mesopelagic zone have developed the most elaborate behavioral strategy for exploiting the marine snow economy: diel vertical migration. At dusk, enormous numbers of mesopelagic fish, representing a total biomass that has been estimated in the hundreds of millions of tons globally, ascend from their daytime depths of several hundred meters to the surface layer, where they feed on the abundant zooplankton and other organisms of the epipelagic zone. Before dawn, they descend again to their deeper daytime depths, carrying in their bodies the carbon and energy of the surface zone's productivity. This nightly vertical migration transfers an enormous quantity of organic carbon from the surface ocean to the deep ocean in the form of fish respiration, excretion, and mortality at depth, constituting what researchers call the biological carbon pump, one of the major mechanisms by which the ocean sequesters carbon from the atmosphere. The lanternfishes, which are the dominant family in many mesopelagic communities, are collectively one of the most biomass-abundant fish groups on Earth, despite being individually small and largely unknown to the general public. And their daily vertical migration is a globally significant ecological process. The extreme energy scarcity of the deep ocean environment has produced in its fish residents not just metabolic frugality, but a pace of life so different from the surface world that it challenges ordinary notions of what a fish's life looks like. Deep-sea fish grow slowly, mature late, live long, and reproduce infrequently. Life history parameters that reflect the reality of an existence where every calorie must be carefully managed and no energy can be spent on accelerated development that is not absolutely necessary for survival. The orange roughy, a deep-sea fish commercially harvested from seamounts in the deep Atlantic and Pacific, was for decades targeted by fisheries that assumed it behaved like shallow-water commercial species, with fast growth and quick population recovery after harvesting. It was only when researchers began aging the fish using growth rings in their otoliths, the calcium carbonate earstones that record annual growth as clearly as tree rings record annual growth seasons, that the true life history of the orange roughy became clear. These fish reach sexual maturity at around 25 years of age, live for more than 150 years, and their populations, once depleted, require generations to recover. Fisheries that collapsed orange roughy populations in the 1980s and 1990s were harvesting a resource whose recovery timescale is measured in human lifetimes. The reproductive strategies of deep-sea fish reflect the same energy scarcity that shapes every other aspect of their biology. Broadcast spawning, in which large numbers of eggs and sperm are released into the water column to meet by chance, is common in many deep-sea species, an energetically economical approach to reproduction that invests minimally in individual offspring in favor of producing very large numbers of them. The probability that any single egg from a broadcast spawner will survive to adulthood in the food-poor deep ocean is extremely low, but the strategy is viable because the sheer number of eggs produced offsets the low individual survival probability. Other deep-sea species have moved in the opposite direction, producing very few, large yolk-rich eggs that hatch into relatively developed larvae with a head start of stored energy, trading offspring number for offspring quality in a strategy that makes sense when the resources needed to develop from egg to juvenile are reliably difficult to find. The reproductive biology of the deep-sea anglerfish represents perhaps the most extreme reproductive specialization in the vertebrate world, one that resolves a specific problem unique to the deep ocean environment. In an environment as large, dark, and sparsely populated as the deep ocean, finding a mate of the appropriate species at the appropriate reproductive time is a challenge that can have no guarantee of solution if the two sexes simply live independently and hope to encounter each other. The anglerfish has resolved this problem through a strategy called sexual parasitism, in which the tiny male, which is only a fraction of the female's size, finds a female using olfactory cues, bites into her skin, and fuses his body permanently to hers. Over time, the male's circulatory system connects with the female's. His organs regress to almost nothing except the testes, and he lives as a permanent attached parasite, receiving nutrition from the female's bloodstream and providing sperm on demand whenever she is ready to spawn. A single female may carry multiple fused males attached to her body simultaneously. The mate-finding problem of the deep ocean has been solved by eliminating the need to find a mate more than once. The deep ocean covers more than 60% of the Earth's surface and constitutes more than 90% of its habitable volume, making it by far the largest living space on the planet. And yet it remains by a considerable margin the least explored environment on Earth. Fewer humans have reached the deepest point of the ocean, the Challenger Deep in the Mariana Trench, at approximately 10,935 meters, than have walked on the surface of the Moon. The deep ocean floor has been mapped at lower resolution than the surface of Mars. The inventory of deep-sea fish species is still growing with each deep ocean survey expedition, and estimates of the total number of undescribed deep-sea species run into the hundreds of thousands across all taxonomic groups. The deep ocean is not a known world that we are monitoring and managing. It is, in the most straightforward scientific sense, an unknown world that we are only beginning to enter. The technology required to access the deep ocean has improved dramatically in recent decades, and each improvement has produced biological discoveries that revise the existing picture in fundamental ways. The development of remotely operated vehicles with high-definition cameras and precise manipulation arms has allowed extended observation of deep-sea behavior that was impossible with the brief bottom time available to crude submersibles. Baited camera systems that can be deployed and recovered autonomously have documented the communities of fish and invertebrates that aggregate around food falls in the deep ocean, providing census data across geographic and depth gradients that were previously inaccessible. Environmental DNA analysis, in which seawater samples collected at depth are filtered and their contained DNA sequenced to identify the organisms that shed it, is providing species inventories from the deep ocean without requiring the capture of a single animal, opening access to the biology of organisms that are simply too fragile, too rare, or too behavior disrupted by collection methods to be studied through traditional means. The fish that have been discovered in the deep ocean through these improving technologies continue to expand the catalog of biological solutions to the problem of living without sunlight. The barrel-eye fish, with its transparent head and rotating tubular eyes. The blobfish, Cycrolutes marcetus, whose gelatinous, near-structureless body is perfectly adapted for life at depth. but collapses grotesquely into the familiar sagging form when brought to the surface and decompressed. The loose-jaw fish, Nalacosteus niger, which can dislocate its own jaw to such an extreme angle that it effectively becomes a net rather than a mouth. The black swallower, Chiasmodon niger, which can swallow prey more than 10 times its own body mass, its stomach stretching to accommodate a meal that bulges visibly from its otherwise slender body. Each of these animals represents a solution to a specific problem of deep ocean life, and the variety of solutions produced by evolution in a single environment reflects both the diversity of ecological niches available in the deep and the power of natural selection to produce functional structures of remarkable ingenuity from the raw material of genetic variation. And so the night closes gently around the deep, as it always has, as it will continue to do with or without our knowledge of what moves through it. The fish of the permanent dark have no awareness that they have never seen the sun, because the sun is not a concept that the deep ocean's biology has ever needed to produce. They move through their cold, pressurized, lightless world with all the competence of organisms perfectly calibrated to exactly that world, hunting by pressure wave and electrical field and the blue-green flash of a rival's photophore, slowing their hearts to the metabolic minimum, waiting with a patience measured in months for the next contact with something edible, living lives that are by any surface measure extraordinarily slow and extraordinarily efficient, and in their own terms, complete. You have descended tonight through more than 10 kilometers of ocean, through the fading light and into the permanent dark, past the gelatinous bodies that float without effort and the enormous eyes that see what human instruments barely register, past the bacteria that light the anglerfish's lure and the red searchlight of the dragonfish, into the cold, slow world where food falls like snow from a sky that is always out of reach. The deep ocean holds all of this in its darkness, the way the night holds everything else, quietly, without fanfare, in the patient certainty that what is adapted to the dark will always find its way. Let your own breathing slow now to the deep ocean's rhythm, long and measured and unhurried. The pressure of the covers over you is a gentle weight, like the dark water that holds everything in the deep in its soft, cold, permanent embrace. The lanternfish are already ascending toward the surface in their million-ton migration, rising through the dark water toward the faint light above. And somewhere far below the deepest point your imagination can easily reach, in water that has never been warm and never been lit, something extraordinary is moving slowly through the black, following a pressure wave that might be food, trailing its own faint blue light behind it into the permanent dark.